In today's screencast, we'll be reviewing the synthesis and reduction of acid chlorides and the synthesis and reduction of acid anhydrides. These are the most reactive carboxylic acid derivatives, and acid anhydrides behave extremely similar to carboxylic acids when in the presence of the reagents talked about in chapter 20. Acid chlorides are extremely malleable and useful intermediates for synthesis of any carboxylic acid derivative. So first we'll be going over the synthesis of acid chlorides. Both of these will synthesize any carboxylic acid. SOCl2 is the most common reagent we see, but PCl5 will also synthesize this acid chloride. So we're going to draw the mechanism out for this one. So we have lone pairs here. Okay. They'll attack the carbon center, kicking off this over here. Now they're coupled. Two chlorides. Next will be the two lone pairs coming down to the silicon and kicking off a chlorine. This oxygen will be positively charged. Silicon will now have a double bonded oxygen and a chlorine. The next step, that kicked off chlorine will come back and attack this carbonyl center, kick off the lone pairs to the oxygen. So the chlorine was a nucleophilic attack. That's what its role was in the mechanism. Okay, it's still coupled, and this next step will decouple these two. So a rearrangement will occur in which the chlorine gets kicked off and the double bond reforms. So this is the acid chloride plus HCl and SO2. That was that mechanism. Okay, so for reduction of acid chlorides, there's two categories, strong and weak. The strong include lithium aluminium hydride, NaBH4, and palladium on carbon with hydrogen gas. These reagents will all reduce acid chloride into a primary alcohol. Now the weak cannot, they're not strong enough to complete the reduction of the acid chloride into a primary alcohol. So it stops at an aldehyde, which is very unique and interesting because aldehydes haven't really been talked about much in the carboxylic acid and carboxylic acid derivative units. So this is a very unique part. And for the mechanism, we'll be using a acid anhydride before we start talking about it, but it behaves in the same way as any other carboxylic acid. So this is how this reagent looks like. And here you see these groups on it. So first, this bond will attack this carbonyl, and this will be formed and lithium will be a spectator metal. And next, it'll expel and create this aldehyde plus salts, lithium and aluminium salts. So that was that mechanism. And that was all we'll talk about in the reduction. Now for synthesis of acid anhydrides, there's two common ways to synthesize it. The first, here we'll move this down. The first is two equivalents of any carboxylic acid. Two equivalents. In the presence of heat, because if not, this will not occur, and an acid anhydride will be formed. The second is a reagent. And this reagent, here we'll take an acid, and this reagent is P2 P2O5. And this acid anhydride will be the product. So those are both syntheses of acid anhydrides. Finally, we'll talk about reduction of acid anhydrides. And earlier I said that acid anhydrides behave just like any other carboxylic acid. So if we take, and we'll draw out the mechanism for amine reduction. If we take this acid anhydride in the presence of a secondary amine, the lone pairs on the nitrogen will attack the carbonyl center and cause this oxygen to be negatively charged, right? And that'll couple this to that. So this one, here we have HHR1. Okay, and just like how we mentioned in carboxylic acid screen record, amines always have to have two equivalents in any reaction that they do. And this is why, because the lone pairs on this nitrogen need to deprotonate, causing this, should move it down here, causing this to be another intermediate. The double bond will form again, kicking off this part, and then the final product will be a secondary amine with a secondary amine with its subsequent R group, and essentially just a salt. Okay, so that was the mechanism for amine. Grignards will reduce any acid anhydride into a primary or into an alcohol, depending on how concentrated the Grignard is, because so this will be the Grignard mechanism, and it will be extremely similar to the mechanism we just drew. So that's the nucleophilic attack. This is now the intermediate formed. Now expelling will occur again, just like the reaction above. Here is a product. Okay, now depending on how much Grignard you use, you can either stop at this or we can keep going. So in a second equivalence of Grignard, the same thing will occur, the nucleophilic attack, and then this will be the next intermediate. Or we can use R double prime too, because that'll make it more clarified. Now an acid workup, we'll use H3O plus. We'll take the lone pairs off this one. And this will be the final product. A tertiary alcohol. And hydrolysis. Any acid anhydride can be reduced to a carboxylic acid using a proton and in an aqueous solution. Lastly, we'll use a reaction wheel to sum up this screen record. And it'll be an acid anhydride reaction wheel. And it'll look really similar to any carboxylic acid reaction wheel, because they behave very similar, if not the same, in most of the reagents we learned about. So first acids will be formed. All right, now this will be the primary amine. NH3, and it'll yield a secondary. Oh, this tertiary amine reagent will yield a primary amine. Okay, now if we use a secondary amine reagent, this will yield a secondary product. And lastly, we'll use ester formation. So that is a small little reaction wheel of some stuff we didn't cover, but still relevant. And so that was chapter 21, carboxylic acid derivatives, specifically acid chlorides and